Okay, today we are going to talk about um, biorefineries. Of course, uh, so far uh, we have discussed a little bit about biorefinery, but we just want to uh, give you a little bit more insight into biorefineries, about specifically classification of biorefineries, how they are classified in terms of nature of the biomass, in terms of type of the, or in terms of attitude to selection of the specific biomass, so that we say primary, secondary, and tertiary generation of biomass conversion. But before we start, anybody can tell me what is biorefinery?
Any process to transferring biomass to valuable materials such as chemicals or energy, electrical energy or heat during some processes.
Yes, that's true. Uh, so it's true. There is a definition here. It is more or less what Kazem mentioned. It's written in French, but I want to just translate it also in English. But people who are better with French, they can just read the lines. So biorefineries are integrated processes or where a product from biomass with a specific technology is produced, but these products could be a chemical product, it can be a biofuel, it can be energy, it can be agricultural material, for example, vegetal fibers, it can be food or even food material that by which you can make food. So this kind of industry, we call it a biorefinery. But there is another definition. It is about forest biorefinery, bioraffinerie forestière. So again, the definition is written here, uh, but you can read the line to understand what it is. I just want to summarize it for you. It is already summarized, but I want to tell you in from my point of view. You know, in some countries, for example, in Canada, in Scandinavian countries where there is a huge amount of wood, forest, for example, you know that already there is a traditional industry that is called pulp and paper industry. So they use woody biomass, like chips of wood, hardwood, softwood, whatever, and they make high quality paper. All these papers, different sorts that you have, they come from wood. You know that. But forest biorefinery is about integration, for example, integration between traditional forest industries like pulp and paper with new biorefinery processes, okay, so that, for example, some residuals like some waste, some people they hate to say waste, they say residual. So let's stick to residual. So that residuals or effluents or whatever byproduct of forestry can be used in a separate biorefinery where you make value-added chemicals as we saw in the first definition, biofuels, whatever. So when we say forest biorefinery, usually they talk about this kind of integration between traditional. So you have a traditional like pulp and paper industry, and you have a new biorefinery. So you take advantage of this pulp and paper industry, You take the you take advantage of facilities, some material, you use it in the new biorefinery in order to have new products, new biofuels, chemicals, many other things. Okay, so this is the definition of forest biorefinery. I hope you understood. So in terms of classification of biorefineries, okay, so it can be, as we discussed, it can be based on type of the product. Uh, so biorefineries could be based on, for example, um, bio-based material that you produce, or some biorefineries are just for making bioenergy. As an example, some biorefineries are to make bioethanol through biochemical processes, and some biorefineries, like for example, combustion, use biomass to make energy, to make, for example, to use make energy in order to make, for example, superheated steam inside the boilers and whatever. But another type of classification of biorefineries is based on nature of the resources that is used. So they classify into uh, green resources, cereal resources, oil seeds resources, and lignocellulosic resources. Okay, so you know that the green resources usually we will talk later. It is about, for example, grass and other type of biomass that are produced in nature seasonal. For example, you know that in the spring, summer, you have grass on the land, but in winter, there is no grass on the land. So, and this is one definition based on nature of the material. Another one is based on the type of the material, of the raw material that you use for conversion. We will discuss about this more. We classify as based on type of the raw material that we use. We say biomass conversion is a primary generation, secondary generation, or tertiary generation. Okay, but is there somebody who can tell me, for example, what is a primary generation of biomass of biorefineries? Just guess. What does it mean, primary biorefinery?
I can try.
Yeah,
I assume that it's the process before using, how to say this. Okay, I assume that the first generation of biorefineries is just like fermentation, just that. And the second generation is when you treat more complex molecules. That's why I understand.
that's
I
why
don't know.
I asked this question because
Excuse me.
I could guess this could be your answer. Okay, cousin, what's your answer?
I think in first generation we can produce energy. In second generation, chemicals, and in third generation we can produce enzyme and antibiotics and stuff like that.
Okay, keep your answers and then see what is the definition. Okay, I could guess this. Your answers would be about generation of the product, but you will see that is the different definition. Okay, but it's, at least it's good that you answer.
I was lucky.
But your answer was not right. But it's good that you answered.
Okay, okay.
So, as I said, there are definitions the um, based on uh, uh, type of the product, either material or energy, based on type of the resource, and based on the way that the raw material is used. Beside this classification, as we are going to discuss at the end of the chapter, um, Another classification is about, it's not classification, but it's just about integrated biorefineries. So you can have maybe two biorefineries, but they are integrated together, for example, or integration between a traditional pulp and paper process and a new biorefinery process. Okay, so uh, as I said, the first classification of biorefinery is based on type of the product. It can be bio-based product or bioenergy. Okay, but always the attitude in biomass conversion, you have to know that it is to make first of all the process techno-economically viable. In in other words, you make the maximum profit that you can make, and you minimize production of waste or residues, and as also in terms of environment, your process is, these days they call it carbon neutral. If you follow the news, everybody is talking about, I have a process which is carbon neutral. Means less generation of CO2 and other uh, contaminations of environment. This diagram just shows a typical biorefinery with maximum valorization. So this is the raw material. Your raw material is undergoes kind of extraction. After the extraction process or conversion process, whatever depends on your process, you have a product with high value and a residual. And this residual can be investigated in the next step of the process. If it is still has some value, part of it, part of its of it that has value will be returned to first valorization unit, and the remaining will go to the next step for heat generation, electricity, fuel, and whatever. I think one of you has marked. I appreciate if you turn off your microphones because I hear myself twice. Okay, so in terms of type of the biomass, as I said, as we said, biorefineries could become classified into green biorefineries, oilseeds biorefineries, cellulosic biorefineries, and so on and so forth. What is green biorefinery? A green biorefinery, okay, of course, when we talk about biomass, always we have in our mind that we are talking about the kind of green biorefinery because biomass is supposed to be a green source of energy. But here, when we say biomass refinery, we are very specifically talking about uh, type of biomass that is seasonal. So the industry is also seasonal, as I said, like grass. So grass, lucerne, immature cereals, and perishable resources. Perishable means resources that exist, but then they disappear in the environment. You know, this kind of biomass are considered as type of feed for green biorefinery. So what happens is that, for example, you can apply for a kind of fractionation on this biomass and make a valuable or valorized product. This diagram is just a typical green biorefinery, just a typical, just an example, not all processes that exist. It's a kind of typical biomass green biorefinery where one of these seasonal biomass undergoes a kind of pressing. So press is applied into biomass. So after press, you have pressed juice and you have pressed cake. So when you press, So the juice will be extracted. The remaining is cake or gâteau in French. So after filtration or by you can have two different phases. So after by having the juice, you can apply uh, in downstream. You can apply biochemical and other physical, for example, processes to produce streams containing proteins, soluble sugars, and whatever, and eventually you make um, fuels, chemicals, polymers, and other materials. And the cake itself also, for example, can undergo hydrothermal processes, enzymatic processes, thermochemical processes, in order to produce other sorts of fuel, energy, and whatever. And of course, uh, after you have juice or cake, and you apply down a secondary kind of processing to these streams, you will have some residues also. So these residues can be used for example, biogas production, like for example, through gasification or gasification or pyrolysis, and you can use them for cogeneration, heat, and power. This reference I have put here is available in Moodle. I really uh, recommend that you study this reference because it talks about different sorts of biorefineries. It's very interesting. Okay, so this is an example of a kind of a green biorefinery applied to Luzerne or alfalfa. Alfalfa is a kind of seasonal biomass. The picture is here. So after you apply a press, you press the biomass, you end up with the juice. You see, the juice itself is still has a green color. It's not just like a watery, fully water. It contains some still chemicals. And you have also gâteau or cake. So as we discussed previously, each of these streams could be used for some other applications. For example, the juice can be used to improve the medium or environment of fermentation. It can be used for the production of enzymes or enzymes in French. And the cake itself can be used for feeding domestic animals, for production of biogas, for example, through gasification, so on and so forth. But sorts of biomass that can be used in a biorefinery are cereals and oilseeds, oleaginous. So when we say cereals, we are talking about raw materials such as, for example, corn, wheat, and rice. And by these materials, you can produce bioethanol, starch, and some other secondary products. And by oil seeds, uh, when oil seeds, as you know, we are talking about grains that are rich of oil, like canola, sunflower, soybeans, and others. Okay, and these are very interesting biomass, but they are full of oil, and you can buy these biomass type of biomass. You can produce biodiesel, and you can use, as you know, you can use them for food products, for human, and even for animals. Okay. In Canada, these type of oilseeds are produced with different rates, as you see, canola, sunflower, and soya beans. You know that Canada is a large country, splendid with different natural resources. So, thanks to nature of Canada, we can produce a lot of oil seeds. But keep in your mind that oil seeds and cereals are a specific type of biomass, and you will see later why I told you to keep them in your mind. If you remember, I said one big advantage, one first use of oilseeds is to produce biodiesel. Do you know what is biodiesel? Anybody can tell me what is the biodiesel or biodiesel? Have you heard of biodiesel or not?
It's essentially any type of diesel carburant that's derived from biological products. Like I know some really old Mercedes diesels, they can run on like biodiesel made from scrap kitchen oil that they used to make fries, and they can make the old Mercedes. They can run on those.
Yeah, good answer. Yes, thank you. Yeah, so you know that diesel is used as I think Michelle, right? Michelle said by or Michael or Michelle, what's your name?
Michael,
Michael, okay. As Michael said, so diesel is a kind of fuel for diesel-driven engines, like old Mercedes, old cars, even these days. But biodiesel is the type of diesel that produce in general from biomass. But as Michael said, some people also produce biodiesel from old frying oils, for example. You know, in restaurants, restaurants use a lot of oil to make French fries and other type of fast food. But what do they do with the oil? They use that oil also. They apply some processing and make biodiesel. So especially 20 years ago, 10 years ago, up to 10 years ago, since when I was PhD student, I remember biodiesel was a very top topic in biomass conversion. Still, it is very interesting, but you will see that it is a bit controversial. Imagine that, let's see, but by the way, let's see how biodiesel can be produced. Let's consider soya or soybeans. Usually you can harvest 2,900 kilogram of soybean per hectare per acre. Okay, and the product, the crop usually contains 11% mass basis water and 19% oil. Okay, 19% oil. But once you have the product, first what you have to do is to apply pretreatment to remove skin. So you have the seeds themselves. But here there is something delicate. As you see in this first step, we call it pretreatment, where we separate grains from shell or skin of the crop. Okay, cook means the shell of the crop. So grain grain of the oil seeds usually contains oil, protein, and starch. Okay, but the shell of these oil seeds, the shell is a kind of woody biomass. So mainly it is cellulose, hemicellulose, lignin, fatty acids, and some fatty acids. So keep in mind that the seed itself is mainly oil, protein, and starch, but the shell is a different type of biomass. But people use the seed itself, not the shell, the seed itself, the seed for biodiesel production. So after the seed is separated from the shell, they apply a special process. In French, they call it trituration, or it's a kind of actually um, grinding of the seeds and followed by kind of press. So they make them into a smaller kind of particles, and then they apply press. I show it like this, but it's not like this. It has a special equipment. Okay, don't get me wrong. So they apply pressing. By press, the oil can be separated from the cake, from the solid part. But if you apply only press, you end up with a high quality oil, but the efficiency is very low. Percentage of the oil that you can extract is low. Okay, so that's why um, some people they don't do press, they do solvent extraction. By solvent extraction, you end up with maximum recovery of the oil. But if you do solvent extraction, the problem is some contaminants, like for example, some solid residues will be transferred to oil phase. Therefore, you have to do kind of purification to eliminate those impurities. After that, after purification, you the main process starts. The core of the process starts where you produce biodiesel, and this process is called trans-esterification. Okay, so in trans-esterification, usually there is a reaction between the oil and methanol. Okay, and the product is called ester methylic. So this ester methylic, okay, just but please keep in your mind, trans-esterification is reaction between alcohol, which is mostly methanol, and the oil. Okay, and the product is ester methylic, and this ester methylic is biodiesel. Okay, of course, after biodiesel, you have to do other purification like distillation. For example, since beside biodiesel, you have some byproducts like glycerin. So you have to separate glycerin from biodiesel, and eventually you end up with this interesting biofuel that is called biodiesel. If you remember, we said per 1 hectare or per 1 acre of the land, production of soybean is 2,900 kilograms. So from this mass, how much biodiesel produce? 500 liter. 500 liter. So if you can do your own calculation by knowing the density of the biodiesel, you see that density of biodiesel is almost 0.9, is similar to oil that we get from petroleum. It has, I mean, in terms of density, it is lighter than water, and it has very good heat value, 37 megajoule per kilogram. Remember, some biomass has, if you remember from previous chapters, heat value of biomass was like 15 to 23 kilogram megajoule per kilogram. Biodiesel has very interesting heat value. Okay, and you see it is very pure, 96.5%, because water content is low. It's less than 1%. I want to emphasize on these characteristics because as you may remember, the bio oil that is a product from from flash pyrolysis of biomass, the bio oil has about 20 to 50% water. So the quality of the fuel, bio oil as a fuel, is very low because it has huge content of water. But in biodiesel, water content is very low. This is the big advantage. Okay? That's why many people they did research on biodiesel production. So this was about soya. Same thing, same process can be applied to tournesol or sunflower. So you have to extract the seeds from sunflower and then remove the shell, the seed from the shell, and then go through all pretreatments, purifications, transesterification, and downstream purification to get the oil. And here you can see it looks like biodiesel from sunflower is more interesting because in sunflower you can produce sunflower itself by a larger volume compared to soybeans. 3,200 kilograms per acre, from which you can produce 1,400 liters per acre. So all more than twice the volume of biodiesel you could produce from biodiesel. And this is interesting. So this slide is kind of outdated slide, since I want you to yourself go and update this slide. It could be your exam or it could be one of your TDs. That's why I didn't put the update here. I want you to yourself, you guys go and uh, uh, get updated information about production of biodiesel around the world. So anyway, as you see, from 2007 up until 2011, there was an increasing trend in production of biodiesel, and especially in South America, like in Argentina and Brazil, production of biodiesel was very high. You know that because of the Amazonian environment in South America, due to the uh, that kind of a specific nature, uh, biomass conversion in general is very advanced. I don't know if Andres, I know you are from Chile, if I'm not mistaken, but I don't know if it's the
I'm
same
from
thing in Chile.
I'm from
Colombia,
Colombia, actually, yes.
Colombia,
But in my country, we are producing. We're actually working with the sugar cane in the
yeah.
south of my country, and if you look in a global, in the earth, in a ball like an earth, it's the same climate that Brazil used uh,
Mm.
corn
So you
culture.
are saying, so so you are saying even in Colombia you have biodiesel production.
Yeah, ethanol actually.
Ethanol, okay,
Yeah,
bioethanol, okay,
yeah.
okay. Bioethanol
In,
is
in
another
this,
process. Okay,
yeah.
I'm talking about, yeah, but about biodiesel, maybe you can share with us later how biodiesel production looks like in Colombia and other South American countries. Because I know over there it is very common. I mean, in general, biomass conversions because of, as you know, because of that beautiful nature over there. So the prediction was that's why I asked you to update this graph. The prediction was the production of biodiesel by 2022 will be much more compared to 2013. Okay, I want you to, as a kind of uh, extra work together in your team to update this information. What is the current production of biodiesel around the world in general? I mean, you can classify in different countries, but depends on how you find information. Another sort of biorefinery, as you already know, is biorefinery based on lignocellulosic biomass or woody biomass. Already you know that by having a woody biomass, inside woody biomass you have cellulose, hemicellulose, and lignin, plus of course some protein and fat and some fat. But these are the three main ingredients, and you can generate many chemicals. As in the previous chapters, we covered what kind of products you can get from cellulose, hemicellulose, and lignin. So I don't want to go to this slide already. You know that and many other chemicals you can produce from lignin, hemicellulose, and cellulose. But now let's talk about uh, classification of biorefineries based on uh, generation. As what is the primary generation, secondary generation, and tertiary generation. So primary generation means that you use directly agricultural biomass agricultural product to make a to make like other product like a fuel or energy, whatever. For example, if you use a biomass that is rich in sugar, okay, okay, and you use it directly by in a fermentation process and make bioethanol. Of course, as byproducts, you make distillers grain or dorage and CO2. And if you use a biomass that is rich in oil, like oil seeds, like um, for example, canola, sunflower, soybeans, whatever, and you apply trans esterification to make biodiesel and a byproduct of glycerol. This is called primary biorefinery. So when we say primary biorefinery, it means you are using directly the biomass, the main part of the biomass, or the biomass that is already very, can say, demanding agricultural product, especially as a food, as a food, you know. And here is the controversial discussions. Primary biorefineries are not interesting at all because you are using agricultural product like wheat, rice, corn, sunflower seeds, whatever, that could be used for to feed people. You know, population of the world is going to be about, I don't know, 10 billion people by 2050. In less than 30 years, population is going to be 10 billion people. So we need to prepare food. And if you use this kind of material as a fuel resource, no. It's not a good way. As shown by this example, from 8 containers of corn, a bushel is a container that has a volume of almost 35 liters. If you use 8 bushels of corn, you can produce almost 22 gallons of ethanol as a fuel. But this mass of corn was enough to feed one individual person for the whole year. No, so you are depriving that one person to make uh, almost 22 gallons of ethanol as a fuel. So this is the controversy. This is the issue with primary biorefinery. Okay, and another issue with biorefinery is that you are increasing the competition to use land because you want to make fuel, so you have to use agricultural land to make fuel. So at the end, you end up with a situation where uh, quality of agricultural land, I mean farming lands or farms in general, is going to be deteriorated. So it's not good. And of course, as I said, you are destabilizing the world demand of food, and that's the problem. So Andres, Kazem, and some other one said, did you understand now what is primary biorefinery?
Yes, sir.
Yeah, this is primary biorefinery. It means you use directly the main agricultural product as a source of fuel, source of biorefining product, which is not acceptable. But uh, so again, so cereals and oil seeds, okay, those kind of biomass are not really desired to be used in a biorefinery. These are because it's very controversial. People don't like it. But What is the secondary generation? Secondary generation of biorefineries. So secondary biorefineries are those that they use lignocellulosic biomass or woody biomass. So the biomass that contains cellulose, hemicellulose, and lignin, as we discussed, like hardwood, softwood, uh, and even regarding other type of agricultural products, their residuals, like for example, wheat straw, corn cob, and this kind of other things. This is any biorefinery that uses this kind of residual of forestry, residuals of forestry or agriculture industry is considered as a secondary biorefinery. And of course, if you have this kind of biorefinery, there are some advantages. First of all, you have much more abundant and diverse raw materials. And second, you are not, since you have a lot of already available raw materials, so you are not going to compete to cultivate this kind of biomass and at the end damage uh, farming land, you know. But of course, since you are talking about this kind of biomass where you have a very diverse kind of nature in terms of composition, uh, technology are still not that mature. You need to have a very kind of comprehensive technology that can accept or can adapt itself to feedstock with different compositions and uh, physical uh, features so that valorization can proceed. So this is the secondary biorefinery. Okay, as discussed before, um, I just want to pass this slide quickly. By having a biorefinery, by having a lignocellulosic biomass, you can apply thermochemical processes or biochemical processes to make heat, to make biofuels, to make methane and bioethanol and some other products. Okay, but let's go back to biodiesel. The case of biodiesel. That's why I told you to keep it in your mind. As you may understood now, I hope that now that you understood how biodiesel is produced. The original source of biodiesel is oil seeds. Okay, but these are not interesting because they are food. But you can make biodiesel from, I mean, from a secondary biorefinery. How come? Let's, for example, uh, if you have a biomass, a woody biomass that undergoes gasification. So by gasification you make syngas, which is hydrogen and carbon monoxide plus other gases, and then you apply conditioning in order to, for example, separate syngas from other gases and other impurities. You can use the syngas and use it in Fischer-Tropsch process or Fischer-Tropsch synthesis. Via Fischer-Tropsch, you can make a mixture of hydrocarbons, and after you do distillation, you can separate diesel from other fractions of hydrocarbon like gasoline, kerosene, and the others. So anybody knows what is the Fischer-Tropsch process? Hazem, do you know what is Fischer-Tropsch process?
Not very intelligent.
Okay, let me ask somebody else. For example, Henok. Henok, do you know Fischer-Tropsch process?
I think it's a conversion of like syngas into liquid fuel.
Exactly. I wanted you to tell me exactly this keyword. It's a one of the chemical processes is called gas to liquid process. Gas to liquid process is could be everything, but one of the most important gas liquid processes is conversion of syngas to liquid hydrocarbons. Exactly. So anyway, so yeah, Fischer-Tropsch is a process that was invented by some scientists. I think they were in Germany in 1920s. That process requires hydrogens and carbon monoxide, and at some temperatures around, I guess, I think if I'm not mistaken, up to 300 Celsius. Uh, Pressure could be atmospheric to or a bit more than atmospheric pressure, where this gas is converted to a liquid. That's interesting. You use two gas and you make a liquid hydrocarbon. Okay. Um, I want you to think about it how it works because see, you have carbon monoxide, it has oxygen. What happens in the Fischer-Tropsch process? It's not the scope of this course, but I want you to know that this is a very important process. But maybe this pass of biodiesel production could be in your exam. If I ask you how, which process do you suggest to make biodiesel from biomass? So I want you to really understand this process. You can have a biomass, you can use it in a gasification reactor, you make syngas, you after you made the syngas, you can apply some conditioning to remove some impurities like sulfur, CO2, whatever, and you then inside the Fischer-Tropsch process, you make you make your chemicals, and then you apply distillation. After distillation, you get your diesel. That's and you see that from 1 ton of biomass, you can produce 100 liters of biodiesel. So almost, if you assume, if you just assume density of both products and feed is one, which is not true, almost it means recovery is conversion 10%. But still, from 1 ton of biomass, make 100 liters of biodiesel. Okay, but I want you to look at these numbers and yourself calculate what is the conversion by knowing density of biomass and density of biodiesel. Okay, so anyway, this is a very interesting process. Okay, so biodiesel could be one example of product from a secondary biorefinery, but many other chemicals can be used from the secondary biorefinery as listed in this picture, like acid succinic, maleic acid, and many others. Okay, just for your information. But now, what the question is, what is the tertiary uh, biorefinery? That's very interesting. Maybe you have heard about microalgae. Anybody knows what is microalgae before?
Yes, actually, it's just algae that are just growing. They're like unicellular. They grow, they photosynthesize. So if you have a big pool, when you have water that has nutrients in it, then it becomes green. That's essentially it. And then they can absorb the photons from the sun, and then you can convert them into biomass. Well, the
Very
sun
good,
converts it into biomass. Yeah.
very good. Yes. So I'm sure all of you, including myself, we have seen algae in our life. When you go to say, when you go, for example, even to the beach, or if you even inside at the bottom of the swimming pool, you have seen some kind of green layer of things, sticky to the wall of the swimming pool, or to the in or at the beach, not the beach, but kind of beside the river banks. Those are algae. But microalgae are very tiny, or I mean micro scale kind of algae that sometimes you don't see them. Okay. But by the way, microalgae are one of the most interesting resources in biorefinery. And the reason that they say troisième génération or tertiary generation is because people started to learn about microalgae as a feedstock in biorefinery after primary and secondary processes. That's why. Otherwise, I mean, they have, it has nothing to do with first step, second step, and third step of biorefinery. No. The reason that they call it is the third generation of biorefinery. So biorefineries that started to use microalgae produce biomass, and then converting biomass to value-added products. So one big advantage of microalgae is that you don't use land. You don't use land. It is inside water. So that's a big advantage of microalgae. So you don't need to do farming. You don't need forest. You know, and theoretically, the productivity of producing biomass and value-added products from microalgae theoretically is very high. Okay, because they can grow easily and theoretically, and of course they are a big source of. We will see later why they are a very interesting source of biomass. And one issue is that these biorefineries are not yet at commercial scale. There are a lot of research and development activities in the field of microalgae conversion to other products. Okay, so you have to do extensive work, and it has been shown that if you really want to make a process profitable and sustainable from microalgae, you really need to make high quality products, and you really need to make almost zero production of waste. Okay, these are just some studies, but theoretically they are very interesting sources of biomass, of also value-added products. So this is about microalgae. Uh, so yeah, these are some pictures of microalgae. This tower in Washington D.C., right? I forgot the name of this area. It's called. It's a. I forgot the name of this area. It's in front of White House. But you see that somebody is collecting algae from this kind of lake, small lake or a pond, and this is another one, another picture of more algae. But why microalgae are very interesting? This slide, in my opinion, is very important. You need to really know why microalgae are very interesting. It's because uh, microalgae, I mean, they have really strong photosynthetic activities, even 10 to 30 times uh, stronger than oilseed biomass, even 10 to 30 times more active in terms of photosynthesis. This is very interesting. So they are very active. So you know that photosynthesis is the process where organisms they capture the light, they capture CO2, and then they start to produce biomass. If you remember first equation, make glucose, for example, in the first chapter. And these macroalgae are really active, and that's very interesting. So in other words,
Professor, excuse
yeah,
me.
yeah,
But I think this is a bit of disadvantages of microalgae, because I remember when we was in the lab, we want to grow the microalgae. They need a lot of CO2 for the growing, and if we couldn't supply this amount of CO2 to the microalgae that we wanted to grow, they going to die and have very difficulties in laboratory when
okay.
we don't have a sunlight and something like that.
Yes, of course. Yeah, we will reach that point. This is a challenge that you need enough sunlight and enough CO2. But once you have it, they are very active. I think you mixed up the message with what you said. Yes, we will see. There is challenge in macroalgae production because they really need CO2 and uh, sunlight. Okay, but once conditions are there, have the required conditions, they are very active. Okay, I know that we will see the challenge later. Don't rush. But that's why we say they are. If you remember this slide, we said theoretically, macroalgae uh, could be a very productive source for biorefinery. But we say always uh, that okay, theoretically, but practically, sometimes you see the process is less than 10%, 10% in practice because of some limitations, as you mentioned. But theoretically, once you have all required conditions, you are 10 to 30 times more active than best biomass like oil seeds. No? But beside their activity in photosynthetic activity, they contain very interesting composition. They contain proteins, uh, fat, and unsaturated fatty acids and glucides. In other words, they are a huge source of oil and sugar. If you remember, we talked about primary biorefineries. In primary biorefineries, people used to use uh, main agricultural crops to make biofuel and bioenergy. And nowadays, nobody want to do that. But microalgae is not the food. Okay, at least so far, I haven't heard that. I know that some Asian food maybe kind of algae is used as a food. Um, I'm not very familiar, but I guess so. But in general, macroalgae are not used as a food, and they are a huge source of oil and sugar. So you can use them and make biofuels very easily. Not very easily, I mean, very productive, in a very productive way, and with less controversial issues. Another big advantage of macroalgae is CO2 capturing. As Mohammed just mentioned, macroalgae requires CO2. Okay, so uh, nowadays many people talk about uh, uh, development of CO2 capturing by macroalgae. If, in other words, if you I don't know if you are following news of killing technologies and carbon capturing technologies. Many people, they do research and development activities to reduce CO2 in the environment. Okay, I know that for I know myself that in France, for example, if I'm not mistaken, Olympic Games of 2024 is going to be in Paris. If I'm wrong, correct me. But I guess it's 2024 or 2028. I guess it's Olympic Games. Anybody can correct me? Olympic Games in France? Okay. I I hope most of you are they do a sport. You are following the sport news. So Olympic Games in France is going to be, I guess, in 2024. And one of the big kind of um, claims that France is going to express at the beginning of the Olympic Games is that Olympic Games is going to be happen at a very clean environment, at a very CO2 kind of carbon neutral environment. And they are doing a lot of, in France, they are doing a lot of efforts to, develop CO2 capturing technologies just for Olympic Games as an excuse. And one of the big projects that even I know Professor Shauki is involved in is to make, is to grow microalgae, is to grow microalgae and use them for CO2 capturing. I know this is one of the interesting projects that in France they are putting a lot of money for it. So microalgae, see, so here we say we are using one bullet, but we get two targets. You use CO2, you use microalgae to capture CO2, so you solve the issue of CO2 emissions. On the other hand, you grow your microalgae and produce, and you convert the biomass of from microalgae uh, produce value-added chemicals and biofuels, bioenergy. That's the advantage of microalgae. So this process, so this uh, picture here shows a kind of schematic of microalgae production. So for making microalgae, you need water, you need CO2, you need sun, you need light. Okay? Not necessarily sunlight. You need light. Okay, and after you make biomass of algae, you do whatever you want. Just an example of just as a comparison between microalgae and other biomass, like a primary biomass, like soya and palm. You can produce uh, 446 liter per hectare of soya and almost 6,000 liter per hectare of palm, but with respect to microalgae, per 1 hectare of microalgae, you can produce 20,000 to 60,000 liter of oil. So this shows how microalgae is very interesting uh, source of biomass. Okay, so there are two ways of producing microalgae. One way, which is the most practical way, is to use special ponds. In French, it's called étangs. They use a special ponds, but they are quite shallow. They are not very deep. If you just look at this pond, for example, you can see that the height of the depth of the pond is maybe less than 1 meter. Okay? So they use ponds and organisms inside these ponds, they are just using the natural sunlight. Okay, they use the natural sunlight and then they grow. Okay, so it's based on a kind of, we call it a ciel ouvert or open air process, kind of, you know. And so the material, organic material here, they capture sunlight and then they start to grow. This process is called photoautotrophy. Okay, so photoautotrophy means a condition that any biological material can produce his own food or his own energy. So this is the way that is done in open air ponds. But it has some disadvantages, some issues. I mean, in this system, the issue is that you have to use a lot of water. It requires a lot of water. Okay, but also usually uh, this process is very sensible to environmental conditions. And for example, if you have special impurities, the growth will not be at the high enough rate. And if you have, for example, microbial contaminants, system is very vulnerable. System organic matter can die. The growth of the microalgae can stop. Okay, so this is because the open air. Okay, so there could be wind, there could be dust. It is exposed to in open environment. So that's why this kind of microalgae production is has some disadvantages. So another type of technology for producing microalgae is by photobioreactors. This is the technology that we are involved in project in France. As I told you, uh, for Olympic Games, they want to reduce CO2 emissions. So photobioreactors are in opposite to open air systems, they are in closed systems. So it's like a reactor, it's a closed system where you have the material inside. It's a closed system. And some advantages of this system is that you can manage the operation of the process. For example, um, in this system, you don't need to use sunlight. You can use fluorescent lamps. By fluorescent lamps, you can generate the UV that you need for the growth of the microalgae. But photobioreactors, uh, technically, they seem more promising compared to open air systems because you can control condition of the reactor because the closed system is not open system. But they are expensive, especially just at the beginning. They are expensive. And as I have emphasized from the beginning of the course, any process development, okay, should be followed by a technical and economic assessment. And if the process is not economic, you cannot do it because nobody gives you money to develop a process that is going to have a negative cash flow. That's why a lot of research and development activities are there in order to, uh, make sure that photobioreactors they can operate and they can be um, economically viable. So, as Muhammad mentioned just at the beginning, a few minutes ago, uh, yeah, he is right. One of the difficulties is light, or having enough CO2. So, for example, I know that maybe I can show you. Maybe I can show you. I know, for example, one specific reactor that now we are designing. to address exactly concern that Mohammed mentioned about problems to gather CO2 and everything and light. We are making a special reactor that is exactly looks like a tree. So we have a reactor, but it looks um, like tree. I mean, it has different branches. Okay, I don't know how. I'm not a good painter or drawer, so you can imagine a tree. Okay, that has many branches, and we apply a fluorescent lamp or even natural sunlight from different sources, but due to having these branches, light can be distributed, across the surface of the macroalgae in order to make sure that they receive enough sunlight or enough light if it is fluorescent. You know, so it is something that is under research and development. People are doing a lot of computational fluid dynamics and a lot of other modeling things. Make sure that integration between the light intensity, macroalgae growth, and some other important uh, operating parameters are optimized. Okay, so it is a matter of uh, research and development. By the way, uh, once you make macroalgae and then you apply kind of folliculations to collect macroalgae and separate them from the water phase, and at the end having the bulk of the macroalgae, you can produce again similar to other uh, biomass resources. You can produce different sorts of biofuels, biochemicals, bioenergy, even food products, pharmaceutical, many other things. You know? But talking about macroalgae is a subject of development and scientific subject of development where many expertise is required. Chemical engineering, biology, chemistry, physics, electrical engineering, many branches, mechanical, many other branches are involved in it. They should be involved. And this is exactly the program that is being run in France. There are different universities and companies not around the world, I can say mostly in Europe and in North America, where they want to really make this process work. So again, as back to uh, concern of macroalgae generation, one issue in macroalgae is light. If you look at this map that shows intensity of uh, sunlight across the globe. Of course, this is kind of average of 1983 to 1994, but you can assume that it still is similar, even though we have we have been facing global warming, but you can assume almost same pattern around the world. You see that around the equator we have a strong intensity of sunlight, but beyond this area, sunlight intensity is not enough. Even if you look at, for example, Africa, north of Africa is okay, but even middle of Africa and south intensity is not good enough. Close to the poles, definitely sunlight is not good enough. You know, so uh, that's why making, I mean, growing macroalgae by, for example, open air system is not feasible everywhere in the world. It requires specific areas. That's why people now do a lot of research and development to develop photobioreactors in order to generate light by fluorescent and some other techniques. In short, there is enough UV energy in the system. And as I said, anyway, talking about microalgae, uh, since the processes are not yet commercial, there are a lot of technical issues to make sure that the process can operate continuously while the process is cheap enough. So a lot of still optimizations are required. But potentially, macroalgae is very, very important source in biorefinery. I forgot to say something in this graph. One big advantage of macroalgae growth, as you see, is production of oxygen. It's very interesting. Oxygen is important in the air, but also oxygen can be used in some industries that use oxygen. For example, again, talking about carbon capturing processes, one process is called oxy-fuel combustion. In oxy-fuel, you don't use air for burning fuel. You use either pure oxygen, which is very expensive, or kind of a mixture of nitrogen and oxygen, where oxygen concentration is more than 40%, for example. Okay, so but because of the oxygen content, uh, because of the quality, I mean, in other words, since making pure oxygen is expensive, most of the carbon capture technologies, oxy-fuel, chemical looping, and others are really uh, suffering from economy of the process because oxygen oxygen separation from nitrogen is really expensive process. So as we are going to talk about process integration at the end of the chapter. If you have, if you have, if you develop a macroalgae, production plant beside, for example, a kind of power generation where you have to burn a fuel to generate energy. Okay, if you integrate these two, it's very interesting because first of all, you know that in power plants, you burn fuel, you produce a lot of CO2. So you use that CO2, okay, for macroalgae. But on the other hand, in macroalgae production, you produce oxygen. And that oxygen can be used for combustion. Of course, it is an idea. We need to do simulation, we need to do technical analysis to see if the rate of oxygen production and even the amount of oxygen that you produce is enough to supply the oxygen of combustion process. So, but I mean, as an idea, it is possible. Okay. So anyway, talking about biorefinery based on algae, once you generate biomass, microalgae-based biomass, we can do similar thing that we could do with other type of biomass. You can produce biodiesel, you can produce biogas, food material, you can make a pharmaceutical, nutraceutical, cosmeceutical products, many other things. So if you want to have more information, you can go to this reference to have an idea of uh, different products you can make from microalgae. This graph here is very interesting. It shows you just as a comparison, how much, for example, biodiesel you can produce for a microalgae in comparison with other types of biomass. You can see that it's almost like more than 10 times more biodiesel that you can produce from microalgae compared to other types of oil seeds. Okay, so this is very, very interesting. I hope you understood the message. Okay, I can give, okay, maybe we can give 5 minutes, or we can continue. Let's finish this chapter. It's just a very short part of the discussion of this chapter, because I don't want to pass beyond 2:30. Some of you have classes or have to leave earlier. It is about process integration. So far, you learned about biorefinery concepts, classification of biorefinery in terms of type of biomass, in terms of generation of biomass, and also you learned that right at the beginning when we talk about forest biorefinery, you learned that you can have integration between a biorefinery and a traditional uh, forest technology like pulp and paper production. So this slide, when you see P and P, means pulp and paper, or pâte et papier in French concept. So um, this so what we are going to discuss now is about integration between a biorefinery and other refineries, other kind of factories or uh, processes that exist. Actually, in process integration in general is a big topic. Cannot discuss everything in the chapter. It's a really big topic, one of the most important aspects in any process development. And before I go to this discussion, for example, now we are doing a research with a company in Morocco where they produce phosphate products like phosphate acid, phosphate-based fertilizers, and many others. Okay, in in that company, they have a lot of byproducts that they don't need it as their main selling products. So they are dumping that product that is called phosphogypsum into ocean. We have recently developed a technology where we claim that phosphogypsum can be converted to a new value-added product, uh, but it has to be really integrated with the conventional phosphoric acid production that they have in Morocco. Integration means like you can imagine like that. Let's say you have a family, mother, I mean parents and some children, and now parents decide to adopt a new child to family. Okay, if you want to adopt a new child to a family, it's not easy. Okay, or I mean the most common example in Canada. Many people, including myself, we immigrated from our country to Canada. We have to now adapt to the environment in Canada in terms of language, in terms of culture, in terms of way of thinking, working, political, social, everything. So adaptation to new environment is not easy. It takes time. It takes a lot of work in order to get integrated. This kind of adaptation means integration. Same thing in industrial domain. and particularly in biomass conversion. As I said, in Canada, we have already a couple of pulp and paper industries. And I don't know if you have heard about FP Innovation. You can go to the website of FP Innovation and you can see what they do. So FP Innovation, for example, is an institute in, I think it's in Montreal. They do a lot of activities related to pulp and paper. Okay, and since already uh, uh, those kind of activities are developed in pulp and paper. So, since there are already many activities, many technologies are developed in pulp and paper industry. Okay, you know that pulp and paper industry, they are dependent on woody biomass. So you can, take advantage of existing technologies, existing facilities, like, for example, utilities like vapor, electricity, water treatment plant, suppliers, contractors, everything that exists, take advantage of, take those advantages and build a new plant for biorefinery to make, uh, products other than pulp and paper, other than paper. For example, biofuels, biochemical, whatever. Just to draw your attention, for example, I remember a long time ago, around 10 years ago, I discussed to president of FP Innovations, and I asked him, what do you think about biomass conversion? And he told me a very interesting uh, answer. He said, pulp and paper industry is really at risk to survive because everything is becoming digital, right? How many of you can buys a paper a real newspaper? How many of you? I think all nowadays most people read everything online, either newspaper, magazines, books, even scientific articles. Everything is becoming digitized. We are, as again, we are in the era of the fourth industrial revolution. Everything is becoming like digital. So there is less demand to pulp and paper products, right? So that's why pulp and paper companies, they want to develop biorefinery products and then integrate between pulp and paper uh, process and biorefinery process. Okay, so this integration, of course, is a huge amount of work, uh, but it is possible, and it is advantages uh, of one big advantage, of course, is to help pulp and paper industries to survive. But also from biorefinery point of view, the advantage is that they use already some, for example, streams like utility streams, as mentioned here, like vapor, electricity, water, chemicals, effluents, others, and even other facilities from pulp and paper process in the biorefining process. Okay, and economically, it has been shown that uh, if such a integration happens, uh, the cost of the biorefinery process can be the cost of such a kind of integrated biorefinery process can be one third uh, of the case if biorefinery was about to develop independently without integration to a pulp and paper industry. Okay, so um, this is the message of integration. But of course, there are challenges. Of course, one challenge is that um, for example, in terms of pulp and paper industry, pulp and paper industry is very well known and developed, but biorefinery processes are still immature. They are not commercially viable yet, and even they don't have secure supply chain. They don't have secure customers, clients, so they cannot make enough money. So it takes time. That's why, as written in this green box, uh, implementation of integration between a biorefinery and a pulp and paper industry should be very gradual. It should be progressive. It should not be right away. It takes time. Yeah, this diagram shows the message that schematically that I just explained. Imagine, for example, you have the pulp and paper process where you use wood chips, water, other chemicals. You know that in pulp and paper, at the end, you want to make um, cellulosic fiber material and products like tissues, plates, papers, whatever, right? But what you can do, of course, you can take advantage of utility systems from biorefined from pulp and paper, like a water, vapor, other chemicals, and also you can use some residuals from this pulp and paper, like for example, some cellulose, some streams that contain cellulose, hemicellulose, and lignin, and use that kind of effluent from from a pulp and paper company, a factory, and use it in a biorefinery. So the biorefinery itself already was using woody biomass, but now it can have also more feedstock from pulp and paper, and continue to make its own biofuels and bioproducts. Okay, so in the next session, we are going to talk about heat integration by pinch technology method. Just to give you an idea, for example, how you can integrate energy between two companies, okay? Or just as an example. But I just want to emphasize that integration between two factories or between two processes, especially if one unit is old and one unit is new, is not that easy. It takes a lot of time, okay? Because um, the old unit is still is running, it makes money, it doesn't need you, but you need him because you want him to invest in your company, and you go away. But you should find a good reason to justify managers of that old process that, you know, if you don't integrate with my process, you are going to lose your market, you are going to lose your customers, so you have no choice. So, you know, I mean, besides technical discussion, there are business discussions also in terms of process integration. Again, next week, anyway, I'm going to talk about process heat integration by pinch method, and I'm sure you will enjoy it. You will see at least how this kind of integration in terms of energy can take place. So already I discussed about these slides. I just want to talk about this last slide about integration. Imagine that uh, you have a biorefinery where you use a specific biomass like sugar cane, okay? And you use this sugar cane to make special products. Imagine that it's a gasification process, okay? For example, so in this process, imagine that in gasification process you make CO2, you know, because you know that in gasification you mostly you make syngas But since after gasification, you have usually another reactor that is called water gas shift reactor, where you convert CO to CO2 in order to increase the volume of hydrogen production. So anyway, you produce a lot of CO2. Okay, so your process is not very clean because you produce CO2. But if you remember, when we talked about macroalgae, we said macroalgae plant requires CO2. So if you integrate the macroalgae plant to this biorefinery plant, so that the CO2 that you generate here can be used for macroalgae production, there you go. You not only you solve the problem of CO2 emission to environment, also you integrate to another process to make macroalgae, and at the end, together you produce a wider spectrum of products, enzymes, ethanol, electricity, sugars, renewable oils, and so on and so forth. If you want to have more idea about this kind of integration, for this case of integration between macroalgae and sugarcane in Brazil, you can go and read this article that already I have put it in Google and learn more about this integration. So it was about the course of today. I hope you got a better idea about biorefinery and integration of biorefinery to other plants. So this will help you to consider um, all these kind of important aspects, I mean, economical, technical aspects for your own project that you are supposed to submit in April.